Sometimes we're asked to compare the acidity of two given hydrogens. For instance, on this molecule up here, we have two hydrogens that are indicated by actually being drawn in, which is, of course, as we know, which is unusual. And so when we draw them, it's really just to indicate where the hydrogens are that we want to discuss. And so this dot here, if I put a dot there, that's actually a CH2. And the third hydrogen is the one that we drew in. Same thing with this carbon right here. That's a CH2 plus this extra H. So we're looking at hydrogens that are on CH3s. And the question is, which of these is more acidic? And of course, this molecule that I've drawn here has no relationship, or at least at first glance has no relationship to any of the indicated molecules on table 3.1. So we can't really use pKa values as much here, but certainly ARIO can help us solve this problem. So the first thing, atom, the two hydrogens are connected both to carbon. So A doesn't help us really. And the next thing is resonance. So let's think about the counter ion for these two hydrogens. So here's the hydrogen on the right side. When we lose it, we get a negative charge. And of course, we don't often or rarely create double anions. I'm just going to save some time in drawing, and we'll look at both these anions as though they were the only anion on this molecule. So the anion on the right, does it have resonance? Can we use resonance? And remember that the four main patterns of resonance, or the five main patterns of resonance, can we use one of those to move this lone pair around? And it's a lone pair, of course, and there's a double bond next to it, so we could use this resonance arrow push, and that gets us to here. I'm going to only draw the first anion now. And we now have, again, a lone pair next to a pi bond. So we could draw a second resonance structure. That gets us to here. So this one does have resonance, this rightmost hydrogen. There is at least two additional structures that helps to delocalize this electron and makes it more stable. We know that negative charges typically lead to instability in molecules, but if we can delocalize this negative charge, spread it out essentially over this region of the molecule, we make that more stable. Now let's look at the left anion, which forms from removing this hydrogen on the left of the molecule. Does it have any resonance possibilities? Well, the first thing we should observe is that this carbon here is sp3, and that means there is no resonance possible for the left anion, because we cannot undergo resonance with an sp3 carbon. We need an adjacent p orbital, whether it's an empty orbital like in a cation, or it's part of a pi bond like we saw on the right side of the molecule. So the left side has no resonance. We'll just say no R. And there is R on the right side. So the more acidic hydrogen is this one that I've just circled. So that's going to be the more acidic hydrogen on this molecule. Another way to ask this question, or to think about it, would be to look at this equilibrium on the bottom of the page. It's basically the same question. Here you see, hopefully you'll recognize this as similar to the right side anion that we looked at. This has the same general shape of it. The rest of the molecule is not there, but molecules don't always look exactly the same. And what we're going to do is take the hydrogen here and trade it, and we can practice our proton transfer arrow pushes too, to get to the anion on the left side of this molecule, which is going to be the same type of anion as we would have formed on the left side of our first molecule. And so now the question is, which side is favored at equilibrium? Well, we already know that there is resonance for this type of anion. It's next to a double bond, it's next to a carbonyl. There is no resonance here. And so we know that this is more stable. And this will be favored at equilibrium. And so we would, if we're asked to circle or just indicate which side is favored at equilibrium, we could circle that side. So basically what we're saying is if we mix this anion with this ketone here, we're going to get no reaction, or very little reaction. Most of the molecules will remain as the starting material.